the air pollutants also affect the climate. And there are some air pollutants, what we call the short-lived climate-forcing pollutants. In short, it's called SLCPs. So if I go from back, pollutants, they are traditional air pollutants, but they have a capacity to force the climate, the second term, and then the first term, they are short-lived. They are short-lived compared to long-lived greenhouse gases like CO2 and the N2O. And that's where the air quality or air pollutants affect the climate. And what are they? What are these SLCPs? So they are aerosol particles. Aerosol particles are composed of many different chemical species, black carbon, organic carbon, and a part of the organic carbon is light absorbing and the other part is light scattering. And then anything I have here in the red color, it is basically they absorb light and the others, they reflect the light. And aerosol particles are composed of so many different components. And at the same time, there are other trace gases. These gases are also traditional air pollutant, and then they are also able to force the climate, but they are also short-lived. So, methane, ozone, and hydrofluorocarbons are those primary interest that we are working on, are the ones which absorb the incoming solar light, and the other one, they ultimately go through the reactions and then reflect or scatter the incoming solar light. So this is where the air pollutants play a role in climate change. So I will keep talking on these aspects, especially the climate warming air pollutants. Those pollutants, they are responsible for global warming. And then, like I said, I'll focus mostly on aerosols. And aerosols can play a role in changing the climate through 4 different processes or mechanisms or effect, whatever we call it. The first one on your left is called the direct effect. The aerosol particles in the atmosphere directly alter the incoming solar radiation in 2 ways. The first one is as soon as the sunlight enters the atmosphere, the particles, some of the particles, they scatter the light back to the space. So in that sense, that would lead to cooling of the surface because not much energy from the sun is allowed to go through the atmosphere to the surface. That's why it will lead to cooling of the surface. At the same time, there are other types of aerosol particles like black carbon, brown carbon, dust. They absorb the sunlight, and that's why they warm the atmosphere. When the sunlight is absorbed in the atmosphere, it leads to cooling of the surface. And this will also depend on where those aerosol particles are. That's too much detail to talk about. But there are 2 direct ways that the aerosol particles affect the sunlight. That's one is scattering back to the space, the other one is absorbing within the atmosphere. And that's called the direct effect. And that's how they change the radiation budget of the atmosphere, whole planet, and that's called the direct aerosol radiative forcing. And the second one is the indirect effect. Indirect effect involves clouds. The aerosol particles are necessary to form the clouds, but if there are too many particles, there will be many particles to share the available water vapor. So what happens is they don't get enough water vapor to condense on the existing particles. So the particle won't grow to a larger size to become a droplet that will ultimately fall out of the atmosphere. So what happens is the particles, the cloud droplets would become smaller. When the droplets are smaller, they are unlikely to precipitate, and they will also have a longer lifetime. They'll just, linger around in the atmosphere. So in that sense, there will be three, effects. The one is the reflectivity of the cloud increases. Basically, dirty cloud will have a higher reflection. It looks brighter. And then in the clean cloud, which has less pollution particles in it, would look a bit darker. We can even see that when you are flying. You can see if you are flying over a dirty, polluted regions, the clouds are normally, brighter. And then that will, increase the scattering of the light back to the space. And the second one is cloud lifetime, because the cloud droplets are not big enough to precipitate. They will just hang around in the atmosphere. So in that sense, the lifetime of the cloud increases. As the lifetime of the cloud increases, so there is a more time to reflect the incoming radiation. And also, like I said earlier, when the cloud droplets are smaller in size, they don't grow enough to become raindrop and they precipitate. That's why they're in the polluted areas or in the downwind of the polluted areas, there is a normally, suppression of the rain. There will be less precipitation coming out of the dirty cloud. So that's called the indirect effect, which involves the, cloud or even a fog. And then the third one is, it involves the particles that absorb sunlight. So what happens here is that if we have a cloud, and within the cloud, if there is light absorbing particle, so that actually absorbs the light and then warms the surrounding, air and leads to evaporation of the cloud. It's called cloud burning. So, that's a one way of affecting it. The other is when there is, light absorbing aerosols in the atmosphere, that aerosol warms the surrounding area and then doesn't let water vapor to condense on. So that basically inhibits cloud formation. And that is called the semi-direct effect. Absorption is involved. At the same time, cloud, microphysics is also involved. So this is called the semi-direct effect. So, and these three are the major effects that happens in the atmosphere. And the fourth one, especially important for our region, is called the snow albedo effect. What happens is when the dirty particles, especially light absorbing particles like the black carbon, brown carbon dust, they get deposited on the surface of the snow and ice, then the surface becomes darker. You can see the debris or the dirty snow, covered here with the black stuff. When that happens, the albedo, the reflectivity of the snow surface decreases, and in that sense, it absorbs more sunlight that hits the surface of the dirty surface, and then that will lead to further melting of the ice, and that's called the snow albedo effect. The dirty particles, especially the light absorbing particles, get deposited on the surface that reduce the albedo and that enhance the absorption of the light and enhance the melting. And there's a double kind of hit on the glaciers and ice because of this kind of warming. The first one is the atmospheric warming that happens over the surface. And the second one is the warming that takes place on the surface or within the snow surface. And that leads to further melting of the snow and the glacier. So these are the four primary mechanisms how aerosol affects the climate. And if you look at the global reports, the most prominent one is the report by the Intergovernmental Panel on Climate Change, IPCC 2013 report. when you look at the report, this summarizes at the global scale, what are the radiative forcing due to different chemical species in the atmosphere. So the one I have here in the red square or rectangle, these are the species called the short-lived climate pollutants, SLCPs, and the CO2, N2O, and some halocarbons are long-lived species. And if you look at their effect, if you look at carbon dioxide, wherever it is, it warms the atmosphere. So carbon dioxide is the topmost global warming agent. And then if you go down here, the aerosols, etc., the black one is from black carbon. So black carbon warms the atmosphere. And also, it warms the snow surface, like I said earlier. And the black carbon is the second largest global warming agent after CO2. And the black carbon is part of the particulate matter, especially, some of us who live in Kathmandu, we can see this black dust or black, smoke, whatever, the black particles, we can easily see that coming out of the, vehicles or the industries and others. So that black carbon is air pollutant. It's harmful for the health. It's a typical air pollutant, but it's, in terms of climate effect, it's the second largest or second strongest warming agent after CO2. But if we look at this, the bars here, the uncertainty bars, the aerosols, especially the indirect effect of aerosol, has the largest uncertainty. What that means is, in terms of carbon dioxide's role in climate change, we know that fairly well. It's warming agent for sure, and then the uncertainty of quantifying its warming effect at the global scale is relatively narrow. So we know that fairly well. But if you look at the particles, it's not known. Sometimes we call it like the wild horse. We don't know what way it affects the climate. Some components like black carbon affects positively in the sense that it warms the atmosphere. The others cool the atmosphere. So which way is the net effect? The net effect is still considered as a negative. It cools the climate, but this is at the global scale. The figure I have here is summarized at the global scale. And the long-lived greenhouse gases are fairly uniformly mixed around the world. There is some kind of gradient across the North Hemisphere versus the South Hemisphere, but it's pretty well mixed, around the world. But the air pollutants are not well mixed. They are higher near or over the areas where they are emitted. For example, in Kathmandu, we have a lot of air pollution because we have so many sources there locally. That's why air pollution is concentrated in that area. So that's what happens. These pollutants are more regionally inhomogeneous. In that sense, effects are more pronounced regionally rather than globally. So even at the global scale, our understanding of aerosol impact on climate is highly uncertain. If you look at over here, in a red circle, on your right, the H means our level of confidence of understanding that effect is high. But if you look at down here, the second one, it's low. Our understanding itself is very low. And that's where, we have a lot of opportunity to, research, further advance the science. And like I said earlier, this is at the global scale. If you look at the regional scale, this uncertainty is way higher. And our level of understanding is very, very poor, especially over the Himalayan region, which is, even in 2013 IPCC report, and and the report the earlier in 2007, this region is classified as a data gap region. What that means is in terms of observations, understanding of climate impact, climate effect, whether it's a greenhouse gas or the aerosols, is very, very poor. That means observations are not intensive over the region. That's why we don't have data that we can use to reduce this uncertainty. So that's why aerosol impact on climate is very, very relevant for the region. Over the globe, it's important. Our understanding is much better, but at the regional scale, it's very poor. Like I said, this region, the Himalayan region, it's a very sensitive region. It has a sensitive ecosystem like glaciers. It has the highest amount of ice, besides two poles. Sometimes it's also called the third pole. And then the mountain regions, as well as the nearby regions of the Himalayas, we have a very large population and then kind of vulnerable population. And this region is double hit. First it's by greenhouse gas induced climate change, and the second one is by air pollution itself. It has health impact on agriculture, etc., etc. That's not part of the topics we are discussing today, but air pollution also has a very prominent impact on regional climate. So it's a double hit by the greenhouse gas induced climate change plus the air pollution. It has a very sensitive ecosystems of global importance, and also has a highly vulnerable large population in the region. So, when we fly in the region, especially when we are flying into Kathmandu, this is what we normally typically see from the air. When you are descending down to Kathmandu, you'll see a large region, large area of the region is covered by this gray, stuff. You can see some cloud here under the mountain, and a cloud over the mountains. But the gray stuff here in those valleys, the mountain valleys, is actually air pollution. And you can see this, as far as you can see from the window. And even in the places where there are no major air pollution sources. So that means this region is, heavily impacted by the long-range transport of the air pollutants, whether it's from other part of Nepal, other part of Tibet, or cross-border pollution coming from across the border. And the Himalayan, Hindu Kush Himalayan region itself is so large, and then you can see the pollution being transported throughout the region. And even in the remote region where it's supposed to be relatively clean, you will see high amount of air pollutants. And then, yes, just to give you some impression of how it looks like, what I call it a disappearing Himalayas. This is a picture I took while descending into Kathmandu. You can see what happens within 2 minutes. It's 1:44 p.m. At certain altitude. You can still see the mountain, and then within a minute, it gets almost blurred, and within next minute, it's gone. So this is the typical scene we'll see in the region. And it's more prominent during the pre-monsoon season, where we didn't have much rain that time, and also a lot of pollution coming from different major sources, and that gets transported over the region, and we get a large scale regional pollution called the atmospheric brown clouds. And then another impression, if we move to the mountain area, it's taken by one of my colleagues from Italy, and see in the morning, you can see Mount Everest here, not so clear. And then what happens as the day progresses with the time-lapse camera, you can see it just disappears. It's not a cloud. It's just the pollution. It's being transported from the other part of the country, plus outside the country. And then in the afternoon, even the Mount Everest area is very close to the base camp, and even in that area gets hazy like this. Okay, these are some of the pictures somebody took. But what happens if you see the region from the space? This is image taken by the MODIS instrument on board ECO satellite or Terra satellite, and the gray stuff here in this red circle in the red square in South Asia, the gray stuff here is pollution. And you can see a large area of Southeast Asia, maybe part of the Middle East. It gets covered by this haze called the atmospheric brown cloud, and that has mostly particles, the aerosol, and also other gases. And if you look at it from certain angle, it looks brown. That's why it's called atmospheric brown cloud. It's not a regular water cloud, it's a pollution cloud. And then, unfortunately, there are a number of studies saying that air pollution in other parts of the world will, start, declining in some part of the world, like, Eastern China, etc. Pollution has already started, decreasing because of, some aggressive measures. In other parts like Europe or North America, air pollution is at a good level, not at the desired level. Air pollution is still a problem in developed countries as well, but it's much horrible in the developed countries. And then, especially in South Asia, air pollution is expected to grow until 2040. In other regions, it will decline. But in South Asia, it will increase. And unfortunately, the Indo-Gangetic Plain, which is the Indo-Gangetic basin here, that includes our southern part as well. It's from Pakistan, India, Nepal, Bangladesh. It stretches over 4 countries. It's a huge area, highly cultivated, heavily populated, and heavily polluted. And it's one of the global air pollution hotspots. And it's expected that the pollution level will still keep growing. That's a major concern locally, regionally, and globally, because it can have effect at the local level, regional level, as well as the global level. Both in terms of human health, agriculture, and climate, and the glaciers, etc. And look at this more zoomed version of that. Another image taken by the satellite. What we see is air pollution from the IGP gets transported towards the Himalayas, and even gets transported across the Himalaya into the Tibetan Plateau. One of the channels is through the river valleys. You can see here Kosi River, and then you can see Gandaki River valleys. Through that channels, air pollution gets kind of squeezed into the mountain regions, and then gets transported over to the cleaner, relatively cleaner areas, remote areas where there are not any air pollution sources, but there is air pollution. That's how the regional air pollution gets transported to mountain regions. And then, like I said, it's not just coming from IGP. Air pollution from different parts of the world has been, tracked, and then they made their way to the mountain regions in the Himalayas and Tibetan plateaus. As far as from Europe, Central Asia, Middle East, North Africa, South Asia, East Asia, Southeast Asia, different fraction of air pollutants, made their way to mountain regions. And though the mountain region, doesn't have major air pollution sources within itself, but the upwind regions have, and that's why it's important to understand what gets transported towards the mountain region, and as well as some regions like the Himalayan foothills, where there are some emission sources Kathmandu Valley, Pokhara Valley, etc. So we need to understand what kind of pollutants are being generated and what pollutants get transported towards the mountain regions, and then what are the likely impacts. And when you look at the aerosol or air pollution impact on different things in the region, I could list easily 18 different things that air pollution impact, aerosols impact. And particularly one we are interested in today is this blue box, weather and climate. There are almost like 12 different aspects that air pollutant, particularly aerosol, can affect weather and then the climate. So including atmospheric heating, like I said earlier, aerosols absorb the sunlight and they heat the atmosphere. And then depending upon where that heating at the layer of the aerosol is, that also change the vertical profile of the temperature, and that we call the atmospheric stability. And once the atmosphere becomes more stable, there's a less chance that pollution gets dispersed. And more recently, there is also studies pointing out that elevation-dependent warming, as you go higher in the mountain areas, the rate of warming is higher, and that is also linked to aerosols. And as I said earlier, when the incoming solar radiation is absorbed or scattered in the atmosphere or back into the space, so there's a less amount of energy reaching to the surface. So that is called the solar dimming. And basically, less energy reaches the surface, and that leads to cooling of the surface. And also redistribution of the heat and moisture, change in cloud and precipitation, and also especially change in monsoon pattern and intensity, melting of snow and ice in the mountain areas. Storms are intensified because of the aerosol particles. And more recently, we have observed that the Indo-Gangetic Plain, including our Tarai region, is facing increasing and persistent winter fog, so that aerosol particles also have a role to play. And also because we have a plain in the south and then we have mountains, so when the air moves towards a mountain because of this orography, the topography, the pollution, the air gets lifted up, and along with that, pollution also gets injected into the upper atmosphere. There's a group working on that. This Tibetan Plateau and the Himalayan region, it's also acting as what we call this the pollution pump that pumps the pollution from the surface into the upper atmosphere. So there are a number of things that are linked to weather and climate to the aerosols in the region. And earlier I showed a couple of pictures, images taken by the satellites. And when you, estimate the aerosol optical depth, which is basically, how this light sees the atmosphere optically, or how the incoming radiation gets, extinct, either by absorption or scattering, so we get less energy coming to the surface. When we integrate that over the whole column, we get what we call the aerosol optical depth. And if you look at the aerosol optical depth from that satellite image, this is what we see. Large part of IGP is red, so it's highly polluted. When the anthropogenic AOD is higher than 0.3, that area is called polluted. So you can easily see, though it has both component, anthropogenic plus natural, but most of the cases, the anthropogenic pollution is higher than 0.3. AOD is higher than 0.3. That means the large region is polluted. That's classified as polluted. And you can see southern part of Nepal, much of Bangladesh. You can see the AOD is fairly high, and that's how the pollution gets transported towards the mountain region and also across the Himalayas into the Tibetan Plateau region. And here are some examples I'm going to show. These are the measurements taken at two sites, one at Paknajol in Kathmandu, and the other one at the Nepal Climate Observatory at a pyramid site. It's near the base camp of the Mount Everest. And you can see this one is the red one is Paknajol. So, on average, like, 10 to 20, even 30 microgram of black carbon per cubic meter. That's fairly high for those of, us working on black carbon. Black carbon concentration, like daily concentration, 30 microgram or so is very high. And you can also see a fairly high concentration of black carbon in the mountain base camp, the Mount Everest base camp area. So that's supposed to be relatively clean, but having like a 3, 4, 5 microgram of black carbon in that area is high. For you just to give an impression, when the Berlin is highly polluted, black carbon will be something like 5 microgram. When it's highly polluted, but sometimes you can get like a 3, 4 microgram of black carbon near Mount Everest. That's the level we are talking about. And also there's the ozone. Ozone is also greenhouse gas, and you can see higher level of ozone in that area as well. So basically, where is that coming from? Where are those pollutants coming from? Even in the areas where there is no major pollution source. So it's basically regional pollution that's being transported across the region. And we have recorded ourselves in some of our studies that even the agro-residue burning in Punjab would have effect on air quality in Kathmandu. So that's how pollution get transported regionally. And then because we are more interested into the climate impact of air pollutants, climate impact of aerosol. So we have done a number of studies. I'll just show you a couple of studies here. So first, to look at, like I showed earlier, even in the Mount Everest area, there's a high level of black carbon, right? Where is that coming from? And what kind of sources are contributing to that? So, our colleagues from China and, ourselves, we collaborated and published a paper. What we look at two transects across the Himalaya, Lumini, Pokhara, Jomsung, and Jungwa in Tibet, and then the other transect is the Kathmandu, Dunche, Nilam, and the Namco. These last two are from Tibet. So when you look at two transects, so what we are surprised here with that even in the mountain areas like Jomsung, Jungwa, Dunche, and Nilam and Namco, the contribution of fossil fuel emissions to black carbon is about 50%. Even in the remote area, 50% of black carbon is sourced from fossil fuel burning. Not there. There are no major fossil fuel burning sources there. Where are they coming from? They are coming from the upwind regions like Kathmandu or other part of the Himalayan foothills and mostly from the Indo-Gangetic Plain. So these are the surface measurement. We want to understand quantitatively what is the pollution level and how much is coming from which source. We need to know that, we need to understand that so that we can later use this information to simulate using the atmospheric model and quantify their individual contributions. And then more recently, we also look into the column measurement. The one I showed earlier are from the surface measurement. They are measured on the ground. But with the other type of instrument, we can also look at the column. You have an instrument on the ground, but that can look up in the sky and see what is in the atmosphere. So we look into 10 different sites, what is called the AeroNet sites, aerosol robotic network. It's a site maintained by NASA. I was also quite fortunate to have two instruments during the campaign in Nepal, and we set up those two instruments at Bode in Bhaktapur and one in Lumbini. So we had a couple of years of data using those instruments. And there are other sites maintained by other groups, and we look into the data and very intensively over 2019, and a couple of them are already published. So what I said earlier, our interest is to understand the aerosols, and particularly light absorbing aerosols, because they are not well understood. There is a huge gap. There's a large uncertainty, and that's where we want to narrow that uncertainty down. And then when you look at 10 different sites, across the IGP, from east, the western IGP to the eastern IGP, through central IGP, and then the Himalayan foothill region, especially Pokhara and Kathmandu, including Lumbini in the northern IGP. Then what we see is the aerosol optical depth. Some of you who have attended, Dr. Rudra Aryal's talk earlier have heard about aerosol optical depth. So it's basically how much aerosol is loaded in the atmosphere, in a very plain language. Or in more technically, how the light sees the atmosphere optically when there is aerosol in the atmosphere. So you can see across the region how the aerosol optical depth changes, from season to season. And then interesting thing here, I'd just like to point out, is these two are Pokhara and Kathmandu. When you look at the aerosol optical depth, they're among the lowest among the 10 sites. You see, they're among the lowest, 0.3 or so. In winter, a bit higher during the pre-monsoon, and again lower. But at the same time, what is called the single scattering albedo, that means the ratio of the scattering to the total extinction. So when you look at that, the Pokhara and then the Kathmandu have the lowest SSA. What that means is the aerosol types in or over Pokhara and Lumbini, the Kathmandu region, have more light absorbing particles. So they're kind of different from the particles we see in other part of the whole region, and that's why we want to know more about what is going on in the Himalayan region, through the Himalayan foothill region. Why aerosols are different there? What happens when they get transported from other regions? And what happens when they get mixed with the local, emissions like from Kathmandu or Pokhara? So this is the thing that's not understood yet. That's why there's a huge potential for doing research. And just what I said earlier, that throughout the region, all 10 sites, they always have AOG higher than 0.3, and that means the whole region is polluted. And the single scattering albedo, especially over the Himalayan foothill sites, indicate that there is a presence of light absorbing aerosols in a higher amount, a higher proportion. And that has an atmospheric warming effect, which I'll show you next. And then, like I said earlier, when the sunlight gets through the atmosphere, a part of it gets reflected back, and then the other part makes its way through the atmosphere to the surface, and a third part gets absorbed in the atmosphere. So that's why we always look at the radiation difference, what we call the aerosol-induced radiation difference, aerosol radiative forcing, at 3 levels: top of the atmosphere, at the surface of the Earth, and within the atmosphere. And whatever is absorbed in the atmosphere, you will see this positive. That means it's absorbed in the atmosphere. That much of radiation is absorbed. So when radiation is absorbed, it will warm the atmosphere. When it's absorbed in the atmosphere, the surface gets less energy, so it gets cool. And these numbers, just to make it bigger so that you can also see, as I just look at these two from Pokhara and Kathmandu, and you can see the amount of radiation that is being cut. Otherwise, it would reach the surface. It's about 50 watt per square meter, seasonally, and that is considered fairly high. So, when we have a bulb, a light bulb at home, we say, okay, this is 4 watt, 10 watt, 100 watt, etc. Per square meter, if 50 watt of energy is cut, it's not coming to the surface. That's huge. That's a huge amount. If you multiply that with the area of the whole country, that much of energy is lost. It's not coming to the surface or absorbed in the atmosphere. When it's absorbed in the atmosphere, it warms the atmosphere. And when, not only from the climate perspective, but when the radiation is cut like this, it has a direct implication to agriculture productivity, especially rice production. So that's why it's also important from that perspective. And this is what we observed, and then we reported in our recent publication. And then, like I said, when the radiation is absorbed in the atmosphere, this will lead to aerosol-induced atmospheric heating. And then that heating, when combined with the global warming because of greenhouse gases plus other mechanisms, then what we come to a conclusion that based upon the earlier studies and modeling, that's also almost like a decade ago, it was said that in the Himalayan region, the aerosol contribution to total warming is about 50%. So 50% warming is because of, let's say, air pollution, and the 50% is from the greenhouse gases. And that this aerosol-induced warming is mainly from black carbon. And then this much of, heating rate is very high. So what we concluded in our recent publication is that at the present context, the contribution from aerosols to total and warming in the region could be even higher than 50%. That needs further studies, including atmospheric simulations using models to better quantify this. But this is the implications we reported in the paper. And then, okay, this is the heating because of all aerosol, they warm the atmosphere, all light absorbing aerosols. But what is the individual contribution of these light absorbing aerosols? That is important to know. And then there is a way, there are recent papers, and they propose ways to estimate that. So when we use aerosol optical depth, that's a total aerosol optical depth. But the optical depth, that's only because of light absorbing aerosols. There are 3 key light absorbing aerosols: the black carbon, brown carbon, and dust. Brown carbon is part of the organic carbon. And then we can use that information, absorption aerosol optical depth, and then quantify or split into contribution of carbonaceous aerosol that includes both brown carbon and black carbon, and then dust, and then further split it into contribution of black carbon and the brown carbon. So this is the first time for the region using the observation data from across the region. There are 10 sites that we have been able to quantify this, and recently published in a good journal, Environment International. So now the next step is to quantify the radiative forcing contribution of this. So that's what we want to understand. And the next step is to quantify their role in changing the temperature. The Himalayan region is warming at a rate that's higher than the global average. But what is the contribution of greenhouse gas to that? What is contribution to aerosol to that? And within the aerosols, there are three major absorbing aerosols. And what is the contribution of each aerosol? The absorbing aerosol. How much black carbon is contributing to, what fraction of the atmospheric warming in the region. So these are the two next steps that we need to understand. That's why, as I said earlier, the whole region is still data gap region. There are a lot of opportunity, potential, scientific questions to explore. and this is where my team is interested in and we're working on. And what we came to conclude in this paper is that black carbon dominates. It's not only the major, but it's the dominates aerosol absorption over this large region, comprising of whole IGP and the Himalayan foothills throughout the year. So that's over 75% of the aerosol absorption is because of black carbon, because it's very efficient in absorbing light. So, but it was not quantified like this earlier. And then, like I said, this is what my group is, NICAS-Himalaya, basically solutions that we are interested in. But before we find the solution, we need to understand the basic science. And a lot of my work focuses on advancing basic science, like what pollutants, when they are emitted, where they are emitted, how much, and what impact they will have. And then the next one is to build the scientific basis that will have, ultimately a situation where we have science-informed policies and actions. The ultimate goal is to support the mitigation measures. So before that, we have to identify the measures. So that is still part of the basic science, transformative impact, and then like Binyasar introduced at the beginning, I don't do only science. I believe strongly that we need to go beyond science if we really want to make change on the ground. So we have to combine science with other aspects so that the solutions are more integrated, and then they are more sustainable. So that's why we keep raising awareness about the pollution, and also build the capacity, especially training master's, PhD, postdoc, students, fellows here, and also engage the key stakeholders. That's a part of the areas I'm interested in: science, policy, and the society interfacing. Unless we interlace these, interacting spheres, if we only provide the physical science information, it's highly unlikely that they will be adopted by the policies. So we need to go beyond science. That's why since 2012, I've been leading a group, and then my goal is to have a more systematic understanding of air pollution and atmospheric science in the Himalayan region with focus on Nepal. Thank you. So I'll be happy to take any questions. If you want to contact me, there are several ways, my emails, or the ResearchGate, etc.
Yeah, thank you very much. Thank you a lot for this wonderful talk with very important information as well as research insights. Now I suggest, Nurapati sir, if you look at the chat box, I can see there is a couple of questions. So please, this is the time for questions, queries. And then if you have any questions, please raise your hand. I can see a couple of hands is there. So we'll address, we'll unmute you later. Nurapati sir. I can see a question here. Dr. Manoj Thapa. Manoj, sir, are you here? Please unmute Manoj sir. Nurapati sir. Or I will unmute. You can unmute yourself, Manoj sir. Yeah.
Thank you, Vanil sir. Maheswar sir, namaste.
Namaskar.
हजुर सरसित भेटेर सरको एउटा स्लाइडमा चाहिँ साउथ इस्ट एसियाबाट पनि हिमालयन रिजनमा एरोसोल पल्युसन आइरहेको देखाउनु भएको थियो। मैले त्यहाँ क्वेसन राखेको एट व्हाट टाइम र कुन लेभलबाट साउथ इस्ट एसियाबाट हिमालयको कुन रिजनमा बढी आइरहेको छ, के छ त्यस्तो केही रिसर्च त्यसको बारेमा भएको छ?
यसमा पर्टिकुलरली यो प्री मनसुन टाइममा मनसुन एक्टिभ हुनुभन्दा अगाडि साउथ इस्ट एसियामा पर्टिकुलरली साउदर्न नर्दर्न थाइल्यान्ड अनि त्यसपछि म्यानमार रिजनमा चाहिँ यो फरेस्ट फायर प्लस एग्रो रेजिड्यू फायरको बर्निङ हुन्छ र त्यति बेला चाहिँ सम pollutants make their way to the eastern Himalaya, not that far into the west, but eastern Himalayan region, some are saying Southeast Asian pollution.
Yes, thank you. And the Tibetan region, but south foothill of the Himalayas, pollution get all about the transfer.
अब लोकल टोपोग्राफी प्लस मेटेरियोलोजिकल कन्डिसनले गर्दाखेरि त्यस्तो भन्न नर्थबाट साउथमा अक्रस द हिमालय पोल्युसन ट्रान्सपोर्ट भएको भनेको रिपोर्ट मैले अहिलेसम्म भेटेको छैन। बरु भन्न तपाईँको सेन्ट्रल एसिया रिजनबाट अथवा इभन अल द वे टु युरोपबाट चाहिँ हिमालयन रिजनमा पोल्युसन आउँछ र त्यहाँ चाहिँ भनौँ न इभन देयर हेभ बिन आइस कोर रेकर्ड्स early 60s, 70s मा जब युरोपमा चाहिँ अझै डर्टी थियो, पोल्युटेड थियो, त्यति बेलाको पोल्युसन चाहिँ हिमालयन रिजनमा डिपोजिट भएको एभिडेन्सेसहरू आइस कोरबाट त्यो राम्रो स्टडीहरू नै रिपोर्ट भएको छ। अनि सेन्ट्रल एसिया रिजनबाट चाहिँ मोस्टली भनौँ डस्ट पोल्युसन चाहिँ आउने टिबेटन त्यतातिर धेरै एरिड ड्राई रिजन भएको हुँदाखेरि डस्ट चाहिँ आउने भनेर रिपोर्ट भएकोहरू छन्। तर नर्थबाट अक्रस द हिमालय साउथमा पोल्युसन आएको भनेको मैले चाहिँ कुनै रिपोर्ट पढेको छैन। अदरवाइज
सस्क्याट प्रोग्राम अहिले पनि रनिङ छ।
सस्क्याट प्रोग्राम अझै पनि रनिङ छ। मेरो निकास ग्रुप जुन हो त्यसभित्र सस्क्याट एउटा प्रोजेक्ट हो। त्यो प्रोजेक्ट चाहिँ म आफै लिड गर्छु। अब विदिन ग्रुपमा डिफ्रेन्ट प्रोजेक्ट डिफ्रेन्ट मान्छेहरूले लिड गर्छन्। त्यो चाहिँ म आफै लिड गर्छु र त्यसको डिफ्रेन्ट एस्पेक्ट्समा हामी काम गरिरहेको छौँ। अहिले चाहिँ मोर हामीले इमिसन र मिटिगेसनमा चाहिँ मोर फोकस गरेर काम गरिरहेको छौँ त्यसको चाहिँ।
Thank you, Manoj sir and Rupakheti sir. I have unmuted Sriram sir. Please ask your question, sir.
Thank you so much, Vinny sir.
Yeah, please.
सुनिन्छ है सर?
एकदमै क्लियर।
रूपाखेती सरलाई धेरै धेरै धन्यवाद, नमस्कार यो ब्युटिफुल वन्डरफुल प्रेजेन्टेसनको लागि। मैले नेपालीमै लिएँ सर। म पनि अलिअलि एरोसोलसँग रिलेटेड काम गर्दैछु, पर्टिकुलरली क्लाइमेट चेन्ज इन एसोसिएसन, लाइटनिङ इन एसोसिएसन विथ क्लाइमेट चेन्जसँग काम गरिरहेको हामीले। र हाम्रो एकजना स्टुडेन्ट हुनुहुन्छ हरिबहादुर केसी, उहाँको एरिया करिब यसैसँग हो र एरोसोल चाहिँ क्लाइमेट चेन्ज र लाइटनिङको लागि एउटा एरिया हो, रिजन हो भनेर हामीले त्यसमा पनि इन्भेस्टिगेसन गर्दैछौँ। सो मैले एउटा सानो क्वेसन त राखेको छु त्यहाँ, यो इन द डेज टु कम सरले चाहिँ भन्नुभएको थियो एउटा स्लाइडमा कि यो साउथ हाम्रो हिमालयन रिजनमा चाहिँ एरोसोलको मात्रा बढ्छ जबकि अरू रिजनमा चाहिँ घट्छ भने त्यसको पर्टिकुलर केही रिजन छ सर?
यो त किनभने हाम्रो रिजन नै वान अफ द फास्टेस्ट ग्रोइङ रिजन्समा पर्छ, स्पेसली इन्डिया। अनि अब अहिले बङ्गलादेश इज अल्सो क्याचिङ अप, नेपाल टु हैन।
बेसिकली इन्डस्ट्रियलाइजेसनकै कुरा गर्नुभयो सरले।
इन्डस्ट्रियलाइजेसन र ट्रान्सपोर्ट सेक्टरको ग्रोथ हैन, त्यसपछि इन्क्रिजिङ पपुलेसन देशमा हाम्रो रिजनमा चाहिँ लार्जली अब नेपालकै कन्टेक्स्टमा हेर्नु भयो भने अलमोस्ट 80% of the pollution in general, I'm not talking about specific pollutant, अहिले पनि हाउसहोल्ड लेभलमा हुने बायोमास बर्निङ फर कुकिङ हिटिङ बाट आउँछ। काठमाडौँ बसेर सुन्दाखेरि हो र भने जस्तो लाग्छ, तर ओभरअल कन्ट्रीमा हेर्ने भने अहिले पनि 80% अफ द पोल्युसन चाहिँ बायोमास बर्निङबाट आउँछ। जुन चाहिँ हाम्रो रिसेन्टली लास्ट इयर पब्लिस गरेको पेपरमा वर्ष काम गरेर गरेको थियो, जुन कुरो अघि दीपक सरले भन्नुभयो लास्ट टाइममा डिपार्टमेन्टमा त्यो हुँदाखेरि जब हामी क्लिनर फ्युल अथवा क्लिनर टेक्नोलोजीमा स्विच गर्नु एक्टिभिटिजले गर्दाखेरि यो रिजनमा चाहिँ पोल्युसन बढ्दै जान्छ। तपाईँहरूले रिसेन्टली सुन्नुभयो कि भएन, अहिले इन्डिया चाहिँ ग्लोबल्ली नै सबभन्दा धेरै सल्फर डाइअक्साइड इमिसन गर्ने कन्ट्रीको रूपमा चाहिँ भन्न आयो होइन। चाइनामा इट्स गोइङ डाउन भेरी फास्ट होइन, तर अब इन्डियामा चाहिँ इट्स ग्रोइङ अप। त्यसले हुँदाखेरि यो अब विभिन्न स्टडीहरूले देखाएको छ ओभर नेक्स्ट फ्यु डेकेड्स पनि एयर पोल्युसन चाहिँ कम हुने सम्भावना एकदम कम छ भनेर, अनलेस वी डु समथिङ म्याजिकल।
यसैमा थोरै मैले सरलाई मैले चाहिँ जानकारी लिन चाहेँ। यो हाई टल माउन्टेनले एउटा चाहिँ अब्स्ट्याकलको पनि काम गर्छ। सो वेनेभर देयर इज अ टल माउन्टेन देयर इज अ माउन्टेन ली वेयर द atmospheric pressure is very high. So the ABC shouldn't be blocked from coming in?
Yes, it does. तर कस्तो भने ABC को चाहिँ इन्टेन्सिटी चाहिँ कहाँ हायर छ भन्दाखेरि साउदर्न फ्ल्याङ्क अफ द माउन्टेनमा छ होइन। इन्डो-ग्यान्जेटिक प्लेन र हिमालयन फुटहिल रिजनमा चाहिँ ABC को इन्टेन्सिटी चाहिँ हायर चाहिँ त्यहाँ छ। त्यसले गर्दाखेरि यो ABC मुभ गर्यो भने कतातिर मुभ गर्छ भन्दा इट गेट्स पुश टुवर्ड्स द माउन्टेन। त्यो हुँदाखेरि अन्डर सर्टेन स्पेसिफिक कन्डिसन तपाईँलाई इन्ट्रेस्ट लाग्यो भने म होला हाम्रो एकजना चाइनाबाट पिएचडी गरेको जोएल लुथी भन्नेले चाहिँ एउटा स्टडी गरेको थियो। त्यसमा चाहिँ under what condition the pollution gets transported from IGP across Himalaya to the Tibet भनेर 2015 मा एउटा पेपर हामीले लेखेको थियौँ। त्यसमा पेपरमा छैन तर त्यसको सप्लिमेन्टरी मेटेरियलमा चाहिँ त्यो सिमुलेसनका रिजल्टहरू कसरी मुभ गर्छ पोल्युसन भन्ने कुरा त्यो सिमुलेट गरेको त्यो भिडियो सहित छ कि त्यो भएर माउन्टेनले ब्लक गर्ने that's why the Himalayan foothill region is so vulnerable. Itself doesn't have much pollution sources except some concentrated areas like Kathmandu or Pokhara Valley, etc.
Thank you, Sriram sir. I have some, probably my internet connection is becoming weak.